satellites are remote sensing tools. Remote sensing just means that if you have an instrument that measures a certain subject or phenomenon, it doesn't have to make contact with that specific subject or phenomenon. It can measure the characteristics of that phenomenon from a distance. There are two main remote sensing tools that we use in meteorology: radar and satellite. Both of these use electromagnetic waves to make their measurements. Electromagnetic waves are just waves that have an electric field and a magnetic field that move through space. But satellites and radar use different types of electromagnetic waves. Now, these waves come in different wavelengths. The wavelength of an electromagnetic wave, or any wave for that matter, is the distance from the crest of one wave to the next. There are several different types of electromagnetic waves, each with a different wavelength, and that creates what we call the electromagnetic spectrum. This is just a spectrum of all the different wavelengths of electromagnetic energy there are. A couple things to note: every object in the universe emits some kind of radiation, whether it's a tree, a house, a car, the sun, a skin cell. Doesn't matter. Every single object in the universe emits some type of radiation. And also, the shorter the wavelength of an electromagnetic wave is, the greater the energy is in that wave. So we'll start at the top here where your longest wavelengths are found, going all the way down to the bottom where your shortest wavelengths are found. Your longest wavelength energy is going to be radio waves. So AM radio, FM radio, microwaves, and radio waves are what Doppler radar uses to measure the characteristics of their targets. As we talked about in the Doppler radar module, the wavelength of energy that's emitted by Doppler radars is on the order of a few centimeters at most. So those are your longest wavelength waves. Those are going to be radio waves. Also, objects like a house, for example, that is going to emit long wave radiation as well in that same portion of the spectrum. Then we go down the spectrum to shorter wavelengths, for example, ultraviolet radiation. That's going to be what the sun emits. X-rays as well. And then your shortest wavelength energy is going to be gamma rays. This is the energy that's emitted via radioactive decay. So if you were to go down to the basement of the Chernobyl nuclear power plant toward the elephant's foot, that's emitting a massive amount of gamma radiation, which is extremely toxic to humans. Now, the only portion of the electromagnetic spectrum that we can actually see with the naked eye as humans is in this tiny portion called the visible portion of the spectrum. These wavelengths correspond to light, and different colors are going to have slightly different wavelengths. So the wavelengths that are coming through in the sky that cause the sky to be blue are going to have a slightly different wavelength than, say, an open flame or fire. That's going to be more of your orange and yellow wavelengths, which are slightly different than the blue wavelengths. Different materials absorb certain wavelengths of energy, including the atmosphere. This is critical to how satellites work. Not all the radiation from the sun reaches the Earth's surface, and not all the outgoing radiation from the Earth's surface goes back out into space. Some of it is absorbed by the atmosphere, while other wavelengths pass through. These particular wavelengths, these portions of the electromagnetic spectrum that are able to pass through instead of being absorbed, these are called atmospheric windows. These atmospheric windows are sensed by satellites, which allows us to get a peek into the atmosphere. We can look at the atmosphere using various wavelengths, each of which allow us to get different information about the weather that's ongoing below. There are 16 different atmospheric windows or wavelengths that pass through that the satellites can sense. These are called bands or channels.
We are currently running a massive sale on our remaining 2027 Storm Chasing Tour seats, so you can book the trip of your dreams and save hundreds or even thousands of dollars. Sale ends Wednesday, August 12th at 11:59 p.m., so don't delay and reserve your seat right now. Link in the description for more information.
Now, there are two main types of weather satellites, the first of which is called polar orbiting. As its name suggests, a polar orbiting satellite orbits latitudinally over the poles. They're situated about 500 miles or so above Earth's surface, and they orbit the Earth about 14 times per day. Polar orbiting satellites are very good at giving us highly detailed imagery of the poles, but not so much the rest of the globe. This is where the second type of weather satellite comes in, which are called geostationary satellites. Geo meaning Earth, stationary meaning not moving. So, geostationary satellites hover continuously over a single fixed location on Earth's surface. Essentially, they're synced to Earth's rotation, so they orbit just once around the Earth per day. This provides us with a lot of advantages. Geostationary satellites can give us continuous coverage of certain regions at all times of the day due to the geostationary nature of the satellite itself. They can record images much more frequently than polar orbiting satellites. Geostationary satellites can give us new images up to every minute. And because they're focused on a fixed location on Earth's surface, we can analyze the actual motion of the clouds below, which of course is highly critical to severe weather forecasting and nowcasting. Now, geostationary satellites orbit at an altitude of about 22,000 miles above Earth's surface, so they're not quite as high resolution as polar orbiting satellites, but with the advances that have been made in the past few decades with geostationary satellites, we can still get very high resolution data of a much larger chunk of the globe than polar orbiting satellites can give us. And the numerous advantages that geostationary satellites give us really outweigh those of polar orbiting satellites. The main satellites we use for weather forecasting here in the US are the GOES satellites. GOES stands for Geostationary Operational Environmental Satellites. Chances are, any of your favorite weather data sites that offer satellite data, they are going to show you data from the GOES satellites. There have been several iterations of the GOES satellites since GOES 1 was launched in 1975. Today we're up to GOES 18 and GOES 19. The GOES suite is occupied by two main global sectors, GOES East and GOES West. Essentially, these are the two main fixed locations above which the satellites are hovering. The GOES East position is currently occupied by the GOES 19 satellite, while the GOES West position is currently occupied by the GOES 18 satellite. Zooming in on our full GOES West sector, you can see how expansive it is. The GOES West and GOES East sectors make up over half the globe, so we have quite the vast expanse that we can analyze using satellite imagery from the GOES satellites. Note that the resolution is somewhat degraded near the poles, but elsewhere the resolution is quite high. And because the resolution is so high, we can zoom in to even smaller sectors that give us a really honed-in look at much smaller regions, which of course is quite useful for severe weather analysis. Typically, in these smaller sectors, new imagery will come in every 5 minutes, but on big severe weather days or for tropical cyclones, we can use the mesoscale floater sectors. These mesoscale floater sectors move around. So, based on where the best chances for severe weather are or where the tropical cyclone is located, these sectors move around. Now, what's nice about these mesoscale floater sectors is that the new imagery comes in every minute, which gives us an even higher temporal resolution look at the data and can allow us to see really intricate changes in these systems over a short period of time. I'm not going to go through all the 16 satellite bands, only the ones that are most important for severe weather forecasting and storm chasing. I'll be using the College of DuPage satellite and radar page for all of the satellite data in this video, but all of the bands will be available through really any source of satellite data that you choose. The first important band for storm chasing is band 2, which is the visible band. If you were an astronaut on the International Space Station looking down at Earth, what you would see with your eyes is basically what visible satellite imagery is. Now, there are actually two different bands of visible imagery. Band 1, which is the visible blue band, has a wavelength of 0.47 micrometers, which is located in the blue portion of the visible portion of the electromagnetic spectrum, hence the name visible blue. Band 2, which is the visible red band, has a 0.64 micrometer wavelength, which is located in the red portion of the spectrum. Whenever you're doing any kind of severe weather analysis, you want to be using band 2, which is the visible red band. Band 1 is good for looking for aerosols, smoke, etc., but clouds don't come through as robustly, as sharply as they do on band 2. Band 1 has a slightly lower resolution than band 2. At the point directly below the satellite, band 1 has a resolution of 1 kilometer, while band 2 has a resolution of half a kilometer. You're going to get slightly sharper imagery with band 2 than you are with band 1. Band 2 has the finest resolution of any of the 16 satellite bands, so it's excellent for severe weather analysis. And what you want to use visible imagery for is to locate clouds. You can look at where clouds are, how they're organized, what their movement is, and other behaviors. And because the resolution is so fine, we can see very small scale features that other bands just can't. For example, we can see things like overshooting tops, outflow boundaries, etc. So again, visible satellite imagery is best for identifying the locations of clouds and assessing their behavior. We can also differentiate the different altitudes of clouds in a visible satellite image, high level versus low level, and the different types of clouds in a satellite image, cirrus versus cumulus versus stratus, etc. In this example, you can see the expansive layer of clouds on the right side of the screen. These are stratus clouds. Stratus clouds occur in layers. The clouds are usually pretty homogeneous within that entire layer, not much change over the entire layer. And stratus clouds are low-level clouds. In contrast, you see these wispy clouds coming in from the west. These are cirrus clouds. And cirrus clouds get their wispy appearance because they are made up of ice crystals. Because they reside at the highest levels of the atmosphere, so cirrus clouds are high-level clouds. Even further evidence that we can determine the altitudes of clouds using visible satellite imagery, you can see the cirrus clouds overspreading over the top of those lower-level clouds, so cirrus clouds, high-level clouds going over the top of low-level clouds. And then you see these puffy clouds at the bottom left of the image. Those are cumulus clouds. Cumulus clouds have that cauliflowery, puffy type appearance. And when those cumulus clouds, which are low-level clouds, grow within an unstable environment, they can become cumulonimbus clouds, or thunderheads. Of course, we're going to talk a lot more about the features of cumulonimbus clouds and what they mean for thunderstorm intensity starting in the next episode. But you can see all the different types of clouds that we can identify on a visible satellite image. Now, when the sun goes down in your area of interest, when it's dark out, visible satellite imagery is rendered useless. Just like if you were to turn the lights out in a room you can't see anymore, same thing with visible satellite imagery. So you cannot use visible satellite imagery at night, only during the day. The next important type of satellite imagery for severe weather analysis is long-wave infrared imagery. Long-wave imagery measures a quantity called brightness temperature, which is the measure of the intensity of electromagnetic energy coming from a source. In simple terms, long-wave imagery estimates the temperatures of the tops of the clouds. From that, we can use long-wave imagery to assess the intensity of storms. More intense storms tend to go higher up into the atmosphere. They tend to be taller. Taller storms have colder cloud tops. Therefore, the more intense the storm is, the colder its cloud tops are likely to be. Now, there are two different bands of long-wave infrared imagery that you can use. Band 14, which is the standard long-wave infrared band, or band 13, which is called the clean long-wave infrared band. Band 14, which has a wavelength of 11.2 micrometers, is slightly more susceptible to absorption from water vapor than band 13, which has a wavelength of 10.3 micrometers. This means that the brightness temperatures measured by band 14 are going to be slightly too cool than what they should be, and slightly cooler than those of band 13. Hence why band 13 is called the clean band. Still, these two bands are basically interchangeable. They're showing you the exact same thing, long-wave infrared imagery and brightness temperatures, but you might see some slight differences in the images between the two bands, and the brightness temperatures shown in band 14 might be slightly cooler than what they should be overall, but it's still a perfectly viable band to use for assessing the intensity of storms. In these long-wave images, your warmer colors correspond to colder cloud top temperatures. So your oranges, reds, and blacks correspond to colder cloud top temperatures indicative of more robust storms, whereas your cooler colors, your purples, blues, and greens, those are indicative of warmer cloud top temperatures and therefore less robust storms. And unlike visible satellite imagery, long-wave imagery can be used 24/7, day or night, because it's measuring temperatures. So it's a good substitute to use at night when visible imagery is rendered useless. The final type of imagery that's important for severe weather forecasting and storm chasing is water vapor satellite imagery. This is comprised of band 8, which is upper level water vapor, band 9, which is mid-level water vapor, and band 10, which is lower level water vapor. Technically, these are still infrared bands, so they're sensing brightness temperature, but water vapor absorbs radiation very well at the wavelengths of each of these bands. So you are able to get a good representation of where there is high and low water vapor or moisture content in the atmosphere. You're going to see lower or colder temperature outputs where water vapor content is high in the atmosphere, and you're going to see warmer or higher temperature output when there is lower water vapor content in the atmosphere, i.e. where it's drier. Each successive water vapor band can see a little bit farther into the atmosphere. Band 8, which is the upper level water vapor band, can see down to about 200 to 300 millibars, which is about 30 to 35,000 feet or so into the atmosphere. This is where the jet stream resides. Band 9, which is the mid-level water vapor band, can see down to about 500 millibars, which is about 18,000 feet in the atmosphere, and it's where we look for troughs and ridges. Troughs are associated with low pressure, ridges associated with high pressure. Troughs are usually a key ingredient in severe weather. And band 10, which is the lower level water vapor band, can see down to about 750 millibars, which is the lower middle portion of the atmosphere. Now there is one caveat. If there's a dense layer of clouds aloft, that's going to obstruct any moisture features that are occurring at lower altitudes. So if you have a thick band of clouds at, let's say, 30,000 feet, well, those mid-level and lower level bands are going to struggle a little bit to decipher any notable moisture features because of that thick band of clouds in the upper levels of the atmosphere. We've already been hinting at it, but one of the main uses of water vapor imagery is to assess atmospheric moisture content. The whites and greens, and even the milky blues you see here, those are indicative of colder brightness temperatures and therefore higher moisture content. While your darker blues and your yellows, those are indicative of warmer brightness temperatures and less moisture content. You'll often see the yellows and even some oranges more so on the mid-level and the lower level water vapor imagery. The oranges indicate very dry air in the lower portions of the atmosphere.
Storm chasing is hard. Get expert help from a live coach. Discord community link in description.
Another good use of water vapor imagery is to identify troughs and ridges. Just as a quick refresher, troughs are those downward kinks in the geopotential height contours, the solid black lines on your upper air maps. Troughs are often associated with low pressure at the surface and rising motion in their exit region, the area to the right of the axis of the trough. So troughs have a lot of the ingredients that we need for severe storm formation. Now you can mainly pick out troughs from your upper air maps, but sometimes they can be quite subtle. Sometimes there are things called shortwave troughs, which are very small scale troughs embedded within a larger trough or just embedded within a belt of zonal or west to east flow. And these can be little extra foci for severe storm development. Sometimes they can be very subtle and they might be difficult to see on upper air maps, but because water vapor is such a good tracer of the mid and upper level winds, we can identify shortwave troughs perhaps a little bit better sometimes by using water vapor satellite imagery, particularly the upper level or the mid-level water vapor bands, band 8 or band 9. So using band 8 here, let's look at this example. So you can see the movement in the milky white and green areas, which of course are your areas of higher moisture content. Those are going to be indicative of troughs and ridges. So we can see one up here in the northern US into southern Canada. You see the counterclockwise rotation of that kind of milky white area and that little band of darker colors there, indicative of drier air. That is a trough. So we can identify that there's a trough right there in the northern plains, upper Midwest into southern Canada. We can also see this big swirl out here over the Atlantic, big counterclockwise swirl there, likely a large trough out here as well. Now, Looking here in the southeast, you see the greens here, which are indicative of thunderstorm activity. Those are kind of spinning in a clockwise direction, which is indicative of a high-pressure ridge that is in place across the southeast. Same thing here in the western U.S. You see the Milky Whites here kind of spinning in a subtly clockwise manner. That can tell us that there is also a ridge here across the desert southwest. Now, one thing here to note is to the south of this ridge, notice this little swirl, little band of darker colors here, and you can see a little bit of subtle counterclockwise curvature in the Milky Whites there. So that is a little bit of a shortwave trough that is located there just to the south of the southwest ridge. And so let's see how we've done. So I'm going to mark our troughs and ridges here. So here is a trough out here in the Atlantic. I'll mark these as L for low pressure areas. Then we have a ridge of high pressure out here across the southeast into the Gulf, high pressure ridge out here across the western U.S., and a little bit of a trough down here, maybe just on the southern side of the ridge, could be a little bit of a trough kind of pushing into the ridge here. So that might look more like this. Just a little bit of a trough there. That could be what we call an inverted trough, which is an area that is like a trough. There's counterclockwise spin, but the winds are going from east to west instead of what is typical in a normal trough from west to east. So I'll mark that as a little bit of a trough right there on the southern side of the ridge. So let's go ahead and put on our 500 millibar winds and height contours here and see how we've done. So I'm going to pause it. And you can see that we've done pretty well here. The trough here across the northern plains, you can see those height contours there, pretty well-defined trough in those red lines there. Those are your geopotential height contours that will indicate the trough. So definitely a clear trough there across the northern U.S. into southern Canada. We see the counterclockwise flow out here. The lines get cut off in the Atlantic here, but you can see that there's a nice counterclockwise flow around that big swirl in the Atlantic. So we've identified that trough there. A little bit of a ridge of high pressure as well, upward kink in the height contours there, with clockwise flow around it across the eastern, kind of southeastern quadrant of the U.S., and then a big ridge of high pressure here over the western U.S. You see the clockwise flow as well, with the closed height contour there over California into Arizona and Nevada. So big ridge there. And we do see a little bit of a disturbance there where we had marked it, a little bit of what we call an inverted trough on the southern side of the ridge. You see the height contour there. I'll take the R labels off, and you can see a little bit of that. So you can see there's still some counterclockwise spin there, even though it is within the ridge of high pressure. So it's basically a trough that's been flipped upside down, and that does also act as a trough would act. Just the winds are going from east to west instead of west to east. So that shows you that you can use water vapor imagery to identify the trough ridge pattern pretty well. And for example, this one here, this is pretty subtle. I'll go to our 500 millibar map on the SPC mesoanalysis page. If you were to look at just this map here, you might miss this little trough, this inverted trough out here on the south side of that western U.S. ridge. If you were to just take a quick look at this, you might not even see that. You can see a little bit of a kink there, an upward kink in the winds there, but it's very difficult to see. But you can see how the water vapor imagery makes it pretty easy to see in that very well-defined swirl there to the south of that western U.S. ridge. So water vapor imagery is a very good tool when you are making a forecast, usually the morning of your severe weather event. It's a good way to kind of show you where the trough ridge pattern is, and if the 500 millibar or the 700 millibar map doesn't really show a lot of shortwaves, but you think there might be some shortwaves in the flow, water vapor imagery is a good tool to use to kind of check your work and see if there are any shortwaves, because water vapor, again, is a very good tracer of the winds aloft and can help identify those shortwaves and make them much clearer than they would be than just using an upper air map. So satellite imagery can allow you to track the forcing mechanism for your severe weather event. Severe storms need a mechanism for forcing for ascent in order to initiate. The atmosphere can be as unstable as it wants, but if there isn't some sort of mechanism to push that air near the surface up into the vertical to tap into that unstable environment, storms are not going to be able to initiate. In most cases, the forcing mechanism for your severe weather event is going to be a trough, in particular a shortwave trough. In the previous episode, we talked about how to use water vapor satellite imagery in order to identify and track troughs and ridges. You can also use visible and infrared satellite imagery to track the arrival of the shortwave. Oftentimes, shortwaves will be denoted by a band of high clouds, typically cirrus clouds, and when the leading edge of that band of high clouds overspreads your area of interest, storms will start to initiate or intensify. Here's a good example of that. Notice this batch of high clouds emanating out of West Texas. That is a batch of cirrus clouds denoting the shortwave. We can see that they're moving from west-southwest to east-northeast, matching the upper level winds. Therefore, we know it's likely a shortwave trough that is being demarcated by these high clouds. And as the leading edge of this batch of cirrus clouds start to overspread the target area, which on this particular day, in this case, it was kind of the western Oklahoma to northwest Texas area. Once that leading edge of that batch of high clouds, i.e. the shortwave, starts to overspread the area, you'll notice that the intensity and coverage of the storm start to increase rapidly, especially across western Oklahoma. You see the leading edge start to impinge upon that area, and thunderstorms start to really intensify over that region.
Safety is king. That's why these rules are not optional. Free ebook link in description.
Switching over to visible satellite imagery, you can see the wispy clouds here. That is that band of high clouds, and as they start to overspread that area of western Oklahoma, those storms start to really intensify there into full-fledged thunderstorms. Now, not all shortwaves are going to be demarcated by these bands of high cirrus clouds, but oftentimes they are, and when they are, satellite is a very good tool to use to track the progression of the shortwave. Visible satellite is an excellent tool to use to identify outflow boundaries. Outflow boundaries are demarcated on visible satellite imagery as very fine lines of clouds, usually small cumulus clouds. And outflow boundaries occur when a storm or storm complex emits a lot of cold air. And the interface between the cold air that the storm complex emits and the warm air that was already in the environment, that is your outflow boundary. Usually there is a wind shift along that boundary as well. Winds to the north of the boundary might be out of the north, pushing out cold air from the storm complex, while winds on the warm side of the boundary might be out of the south or southeast, for example. The winds are coming together along the boundary, which forces air to rise, so you get small little bands of cumulus right along that interface between the cold air and the warm air, and where those winds come together. Outflow boundaries are important in severe weather forecasting and nowcasting for a couple of reasons. Number one, because winds are converging a bit more strongly along the boundary compared to elsewhere, you can have actually a better chance of just initiating storms along the boundary. And number two, supercells that can anchor to and track along an outflow boundary may have increased chances of producing tornadoes because outflow boundaries have enhanced low-level wind shear and vorticity, a fancy word for spin, along them. So supercells can tap into that enhanced low-level shear and can ingest the vorticity along the boundary to have increased chances of producing tornadoes compared to storms that are not anchored to the outflow boundary. Now, not all outflow boundaries are optimal for increasing tornado potential with storms that track along them. You want your boundary to be slow-moving or stationary. This gives the storm a better chance of actually latching onto and tracking along the boundary. And you want your boundary to be oriented parallel to storm motion. Again, this allows the storm to actually track along the length of the boundary, tapping into that increased low-level shear and vorticity to increase tornado potential. Fast-moving or surging boundaries are not optimal. They tend to undercut any storms that fire along them. The storms immediately go to the cool side of the boundary and therefore become what we call elevated above the low-level, stable, cool air mass. Elevated storms are generally unable to produce tornadoes. Slow-moving boundaries tend to happen when your temperature gradient across the boundary is fairly low, meaning there's not a big difference between the temperatures on the cool side of the boundary and the warm side. Usually when there is a big temperature gradient between the two sides of the boundary, that cold air is going to win out and really push that boundary and allow it to surge, which again is unfavorable for storms latching onto the actual boundary. Also, if you have a lot of persistent regenerative convection on the cool side of the boundary, that's going to also allow the boundary to surge quite a bit. Those storms are going to continue to produce outflow, which adds to the boundary and allows it to continue to surge. But if that convection tends to dissipate with time, that is going to allow the boundary to eventually slow down or even stall, because that outflow source that continues to push the boundary along is no longer there. So even if you have a boundary that is being forced by a convective complex, if that complex tends to weaken with time or dissipates altogether, that's a good sign for your boundary eventually stalling at some point later on. Let's take a look at this example here. So here is our boundary, clearly defined by this band of clouds emanating from a pretty stout complex of convection, much of which still ongoing out here across the North Texas vicinity. But notice how this portion of the boundary was pretty free and clear of convection on its cool side. So that might start to give you a little bit of a hint that that portion of the boundary may eventually stall out. This portion here to the east, where the convection was continuing to fire to its north, that was likely going to continue to sag. But because we had a lack of convection on the cool side of the boundary farther west, and also the fact that we had clear skies both on the north and south of the boundary, leading to a decreased temperature gradient from the cool side to the warm side of the boundary, as both sides of the boundary were subjected to strong surface heating. That would mean that there's mounting evidence that that portion of the boundary might stall out a little bit later. And sure enough, you see still a little bit of south movement there, but eventually we go into the afternoon here, and that boundary kind of stalls out, really slow moving right in this area here. And given that storm motion was to the east or east-southeast, that was going to parallel any supercell's motion that tried to track near the boundary. And sure enough, supercells went up along the boundary and tracked right along it, and that supercell there became tornadic as it tapped into that enhanced low-level shear environment along the boundary. Now, a couple of notes. Not all boundaries will show up on visible satellite imagery, and some boundaries that become more diffuse with time may actually disappear from visible satellite imagery going into the afternoon of a severe weather event. Neither of these mean that the boundary is not there or has dissipated completely. Always use multiple factors to confirm the location of a boundary. If you're unsure of whether a fine line on visible satellite imagery is a boundary, or maybe the boundary is really subtle and you can't really see it on visible satellite imagery, make sure to look at other factors like radar, surface observations, etc. to confirm the location of the boundary. Another feature you might often see in visible satellite imagery in the lead up to storm initiation, and sometimes during and just after storm initiation, are cloud streets. Cloud streets are these linear bands of clouds that you see in the image right here. These are the result of horizontal convective rolls, or HCRs. Horizontal convective rolls are adjacent vortices oriented horizontally that rotate opposite one another, and where the winds converge in between rolls, you get these cloud streets where the air is forced upward. Now, these cloud streets are indicative of lingering stability in the environment. If you see an area with these cloud streets in it on satellite, that tends to mean that the area has not destabilized fully yet. There's a little bit of stability left in the low-level environment. Of course, we want an environment that's fully destabilized in order to get the most robust storms. So if you see storms that are moving into an area where these convective rolls are prevalent, that usually is a sign that the storms might struggle with low-level stability issues and may be elevated. Again, that means that it's elevated above a stable layer near the surface, which is unfavorable for tornadic activity. Oftentimes you will see these cloud streets dissipate as surface heating continues, and the further you get into the afternoon, which signifies that the atmosphere is becoming more and more unstable. So the typical progression you might see on visible satellite imagery in the lead up to convective initiation starts off with a cumulus field, which is just an area where cumulus clouds start to develop. There'll be these kind of fair weather, small cumulus clouds And the area can be larger than this one you see here. It can be smaller. It can be just a few cumulus clouds in a very localized area. Or it can also include some of those horizontal convective rolls or cloud streets we just talked about. But overall, the first step toward storm initiation is for a cumulus field to develop. Then, as the atmosphere becomes more and more primed for storm initiation, some of those cumulus will become what we call agitated. Notice in this area here, the cumulus have become a little bit better defined, a little bit more vertical in nature, going from those small fair weather type cumulus into more cumulus congestus, which is that real cauliflower looking cumulus cloud with vertical extent. Not a full-fledged cumulonimbus cloud or thunderhead, but definitely well on its way. So these are agitated cumulus. It's a sign that the environment is becoming more and more favorable for storm initiation. And then once the atmosphere is fully destabilized and the forcing mechanism in question arrives, then you'll see full-fledged convective initiation. Those clouds will become more and more agitated until they become full-fledged thunderstorms or cumulonimbus clouds, as you see here. Now, before that happens, sometimes you will start to get actual cumulonimbus clouds to develop, but the atmosphere might still not be ready for full-fledged, persistent, sustained thunderstorm development. In that case, you might see what's called an orphan anvil. So watch this cumulus congestus down here. It starts to develop into a full-fledged cumulonimbus cloud, but then it dies off, leaving just the anvil in its wake. This is called an orphan anvil. What happens is the environment may be a little bit too stable still, a little bit capped, and so thunderstorms try to go up. Maybe the forcing mechanism has arrived, but maybe it's not quite strong enough to really push those updrafts through the capping inversion. So the storms will try to become full-fledged thunderstorms, but then the updraft dies off, leaving just the anvil in its wake, which is an orphan anvil. So this is a sign that your atmosphere might not quite be ready for storm initiation, but once it does, you'll see those agitated cumulus go from that agitated phase right into the thunderstorm phase when you have sustained thunderstorm development and cumulonimbus clouds, as you see here. And here's another example. We start off the day with quite a bit of thick stratus across the area of interest, and then off to the west we eventually get a cumulus field to develop there in the Texas Panhandle area. The cumulus persist for quite a while. They get a little bit agitated right in there, and then eventually we get full-fledged thunderstorm development as we became fully destabilized in the afternoon. Another tool you can use to monitor for storm initiation is the day cloud phase product. This is not a single band or channel. Instead, it uses a combination of multiple bands to come up with its output. What the day cloud phase product does is, starting with a combination of information from band 2, which is the visible red band, band 5, which is the snow and ice near infrared band, and band 13, which is the clean long-wave infrared band. It uses information from all of these bands to come up with differences in the reflectance of clouds. Reflectance is basically just a measure of how much light clouds are reflecting. This allows us to see increased contrast between clouds of different phases, basically clouds that are made of water versus clouds that are made of ice. As we've talked about before, clouds that grow higher and higher into the atmosphere get colder and colder, therefore fostering more ice production. So taller clouds are going to have more ice crystals than clouds that are much lower in height. So that allows us to see where cumulus clouds are becoming more robust. Now, this is the full breakdown of all the color schemes in the day cloud phase product, but we really want to be focusing on the blues and greens and yellows. Cumulus clouds that are transitioning from lighter shades of blue and green to bolder shades of green and even yellow and orange indicate that those cumulus clouds are undergoing vertical development and seeing an increased presence of ice within them, which of course is a hallmark of strong updrafts and robust storms. Here is an example. Notice how these clouds at the top left corner of the screen are comprised of mostly light blues and greens, which means that they are full of mostly water droplets. This suggests that they are not all that tall, not all that robust. But watch as they move off to the east. They take on a lot more of those greens, yellows, and oranges, indicating that they are now quite full of ice crystals. That means that they are a lot taller, a lot more robust in nature. Here's another example from this same loop. Keep your eye on these developing cumulus here in the pink circle. Watch as initially they take on a lot more of those greens and blues, indicating that they are lower level clouds, not all that robust. But this one up here starts to take on a little bit more of those yellows and oranges, meaning that that is a little bit more of a robust updraft. So this is a good tool to use to maybe, if, in a situation where you have a lot of updrafts that are trying to initiate, this is a good tool to help you see which ones are becoming more robust more quickly. The ones that have more of those yellows and orange colors, those are going to be your more robust updrafts, more ice crystals in those updrafts, meaning that they're taller and more intense. As its name suggests, the day cloud phase product can only be used during the daytime because it's drawing in information from band 2, which is the visible satellite band. It cannot be used at night. If you try to use the day cloud phase product at night or when the sun angle is low, so right before sunset, for example, your output is going to be artificially tinted red, which is not going to allow you to differentiate between different cloud phases. We can't see exactly what severe hazards a storm is producing from satellite imagery like we can on radar, but severe storms do tend to display some certain features and signatures, and that can help you out in the field when you're trying to determine which storm to target or see which storm is most intense. Let's say you're out on a storm chase in western Oklahoma, you're sitting and waiting, and then multiple storms begin to fire in your target. Your job is to figure out which of these storms is going to be most intense and which of these storms you want to target. And as you can see, there are multiple storms firing in our target area, but there's really not a ton of difference among them just looking at radar. You see the storm here north of I-40, the one just south of I-40, and then the southernmost one down there. Really not a ton of difference between these storms just looking at the radar. That's where infrared satellite comes in. Infrared satellite measures brightness temperature, essentially an estimate of the temperatures of the tops of the clouds. Taller, more robust, more intense storms tend to have colder cloud tops, those oranges, reds, and even blacks you see on infrared satellite imagery. So in these situations in which you have multiple storms to choose from, infrared satellite is a great tool to use to identify which storm is perhaps your target storm, which storm is most intense. And you can do that by comparing the cloud top temperatures of each storm. You're looking for the most persistent, coldest cloud tops. So in our western Oklahoma example here, you see all of our storms lined up in western Oklahoma. All of them are displaying fairly cold cloud tops, but watch that southernmost storm here. It seems to display the coldest cloud tops for the most extended period of time, even showing some of those black colors indicating very cold cloud tops, while the cloud tops of the other storms seem to be warming a little bit, indicating weakening. So this would give you a clue that that southernmost storm would be the one you'd want to target. It seems to be the most persistently robust storm of the bunch and would have the highest chance of producing severe weather. Now, it's fairly common to see fluctuations in which storm has the coldest cloud tops. As you see here, all the storms have some sort of cold cloud tops. They kind of trade off for a little bit. Initially, this northernmost storm seems to have the coldest cloud tops. Then it transfers to one of the middle storms there. But that southernmost storm has the most persistent, coldest cloud tops, those very cold cloud tops, which are the coldest that we've seen of any of the storms, getting into those black colors. And it's had that for the longest amount of time. So that storm is the most persistently robust, and that would be a sign that you might want to target that particular storm. Now, speaking of this small spot of very cold cloud top temperatures within the anvil, that is indicative of a feature called an overshooting top. And if you've ever seen a thunderstorm from a distance before, you've probably seen an overshooting top. Thunderstorm updrafts are quite intense. The flow within them can be traveling at 100 miles per hour or more in some of the strongest storms. But when the updraft hits a layer of the atmosphere called the tropopause, it flattens out. That's what gives the cumulonimbus clouds their anvil-type shape. What happens is the updraft goes up and up and up until it hits the tropopause, above which is the stratosphere. In the stratosphere, temperature tends to increase with height, which is unfavorable for convection. So the updraft goes up, hits that tropopause, which is the interface between the troposphere, where most of our weather happens, and the stratosphere. It hits that tropopause and flattens out because it just can't go up anymore as the temperature of the environment starts to increase with height. But the updraft is moving so rapidly in some of the strongest storms that its momentum carries it up into the stratosphere just a little bit, and you get a little bit of a dome-shaped bubble on top of the anvil, which denotes the portion of the updraft going into the stratosphere. That is your overshooting top. So an overshooting top is usually a sign that a storm is quite intense. Overshooting tops, as we mentioned, show up well in infrared satellite imagery as these kind of dots of extremely cold cloud top temperatures within the anvil, but they also show up well in visible satellite imagery as these kind of bubbly areas that seem to be rising above the rest of the anvil. This will also be co-located with the signature in infrared imagery. This is a pretty textbook example of an overshooting top, particularly with the southern storm. The very bubbly area right there, rising above the rest of the anvil, is your overshooting top, which is co-located with that darker area in infrared satellite imagery. Another signature you might see in infrared satellite imagery that indicates an intense storm is the enhanced V signature. The enhanced V is the satellite equivalent of the V-notch radar signature that we talked about in the Radar Foundations module here in the Chaser Academy. The enhanced V is a V-shaped band of colder cloud top temperatures that surround the overshooting top. So here is your overshooting top right there, and then you have this V-shaped or boomerang-shaped band of colder cloud top temperatures surrounding that overshooting top. The reason an enhanced V signature forms is because the updraft acts as a barrier to flow. Just like, say, a mountain acts as a barrier to flow, so does a strong updraft. So say, for example, we're looking straight down at a thunderstorm updraft. Air can't go through the updraft, so what happens is it gets diverted around the updraft, and that's how you get that enhanced V signature, that V-shaped band of colder cloud tops around the overshooting top. Again, an enhanced V signature is a good sign that your storm is quite intense. In fact, it has been shown to be an excellent precursor to the onset of severe hazards within storms, generally with a median lead time of about 30 minutes, meaning that the development of the enhanced V usually precedes the first severe weather hazards occurring within a storm by about 30 minutes or so. This is a textbook example, very clear example of an enhanced V signature. Again, here is your overshooting top, and here is that band, boomerang-shaped band of colder cloud top temperatures surrounding the overshooting top. And here are a couple more examples. There is your overshooting top right here, band of colder cloud tops surrounding that overshooting top. And a slightly more subtle example, this storm in the upper right-hand corner of the image. Notice your area of coldest cloud top temperatures there, and this band of orange colors surrounding that in that V-shaped manner. That is your enhanced V. Now, not all severe storms produce enhanced V signatures, but a good percentage of them do, and you can be sure that if you see an enhanced V signature on infrared satellite imagery, that storm is quite intense and could very well be producing or produce severe weather in short order. Another signature that's related to the overshooting top is the Above-Anvil cirrus plume. These are areas of cirrus clouds that exist several kilometers above the anvil of a thunderstorm that are caused by gravity waves as the updraft or overshooting top penetrates into the stratosphere. I always use the analogy with gravity waves of throwing a rock into a calm pond. As the rock enters the pond, it's going to make ripples that move outward from where the rock went in. Same thing with gravity waves, and in this case, it is when the updraft or overshooting top penetrates into the stable layer of the stratosphere. As it does that, that energy is kind of dispersed outward, and you get gravity waves. And this sometimes allows a plume of cirrus clouds to form, and that is the Above-Anvil cirrus plume. And in this image here, which is taken from Bedka et al. 2018, the white dashed lines indicate examples of Above-Anvil cirrus plumes with visible imagery on the left and infrared imagery on the right. Above-Anvil cirrus plumes can be pretty difficult to identify on satellite imagery. They're easier to see in visible satellite imagery. Notice on the left here in the dashed white outlines the kind of wispy band of clouds that's emanating and flowing downstream from the overshooting top. That is your above-anvil cirrus plume. Same thing down here with this southern storm. You have your overshooting top here, and then the wispy area of clouds within the white dashed outline. That is your above-anvil cirrus plume. They can also be seen in infrared satellite imagery, but there's not really a standard signature that you'll see in infrared imagery when an above-anvil cirrus plume exists. Oftentimes they'll be demarcated by an area of warmer cloud top temperatures downstream from the overshooting top, and oftentimes they'll be embedded within the enhanced V signature, as you see here with the southernmost storm. But as you notice with the northern storm, there really isn't a significant area of warmer cloud top temperatures within the area of the above-anvil cirrus plume. So infrared imagery can be a little bit wishy-washy as far as showing a signal of an above-anvil cirrus plume, but most often you're going to be seeing them in visible satellite imagery, as you see on the left. Here are a couple of examples of above-anvil cirrus plumes on visible satellite imagery. This first one is actually from the infamous Gerald, Texas F5 on May 27, 1997. The supercell that spawned the Gerald tornado is the southernmost storm, so keep your eye focused on that storm. You can clearly see the overshooting top in the anvil there. As we go forward with this loop, you can see a very defined plume of wispier clouds emanating downstream from the overshooting top. That little bit of wispiness there downstream from the overshooting top, that is your above-anvil cirrus plume. Here is another example. Keep your eye on the southernmost storm here as well. There is your overshooting top. So look just to the east of there as I play the loop here. You'll see a well-defined area of those wispier cirrus clouds that flow downstream from the overshooting top. You can really see it in this image here, that wispy plume right in there. That is your above-anvil cirrus plume. This example is pretty well defined. Again, they're not always going to be this well defined, but these two examples were pretty textbook examples of above-anvil cirrus plumes. Like overshooting tops and enhanced V signatures, above-anvil cirrus plumes indicate that a storm is very robust. In fact, above-anvil cirrus plumes tend to only exist in the most robust storms with the highest and coldest of cloud tops, and oftentimes supercells will display above-anvil cirrus plumes. And similar to the enhanced V signature, the lead time between the first signs of development of the above-anvil cirrus plume and the onset of severe weather hazards from a given storm tends to be over 30 minutes on average, so it's an excellent precursor to the onset of severe weather. And finally, sometimes you may see bands of cumulus clouds flowing into a thunderstorm on visible satellite imagery. This is a sign that the storm has healthy, warm, moist inflow. Taking a look at this example here, focus your eyes on this southern storm here, and on its southwest flank you can see a band of cumulus leading into the storm. And as it matures and becomes a little bit more intense, you can see all these bands of cumulus flowing into the storm on its southwestern flank. All of these clouds are flowing into the storm, denoting that the storm is experiencing healthy, warm, moist inflow. These bands can include the flanking line of a storm. The flanking line is a series of updrafts that feed into the main updraft of a supercell. If you've ever chased a supercell, you've probably seen a flanking line, and it looks something like this from the ground. That series of cumulus clouds that feed into the updraft base, the main updraft base of a supercell. And these can also involve just inflow feeder bands that flow into the supercell. In any case, these all promote supercell longevity. These are persistent sources of energy and really fuel that feed into the supercell. In terms of a flanking line, if for some reason the main updraft starts to dissipate a little bit, the next updraft in the flanking line can then take over and become the new dominant updraft. So anytime you see a look like this on satellite, that is indicative of a very intense supercell with healthy, warm, moist inflow. And this supercell, in this example, did go on to produce all severe hazards, including a few tornadoes.
Remember to check out those links in the description below, and then watch another video.